In this video, we are going to demonstrate a minimum example of a diffusion problem in a pipe. We will work with the diffusion equation, which will look like this. So we have a differential equation describing the change of the concentration over time, which is a function of the diffusion term here. The diffusion term is the second order derivative with respect to the space dimension. So the spatial dimension will be x and the time dimension is t here, and concentration, which is a state variable, we call it c. To start with, we can imagine that we have an empty pipe demonstrated here, and we have an initial concentration of 10 milligrams per cubic meter of some toxic gas on the left side of the pipe. Imagine that over time this gas will diffuse to the other end of the pipe. We will try to simulate that now and write a simple code for that. So the first thing we have to do is we have to define the length of the pipe. We could say this is 1 meter. We then split this pipe up in perhaps 100 pieces. So we say that dx is equals to 0.01 meter, 1 centimeter. So this is our space step size. And we can then make the whole X grid, we call it, which we do NP arrange. Now we also need to define a constant, the diffusion coefficient. D for a gas diffusion in another gas, it is approximately this much in square meters per second. The next thing we have to do is we have to make a function that calculates the derivatives. And you have to imagine that you have an X grid, and for each node on this X grid, we will define a differential equation or the derivative that explains how the concentration changes with time at that point on the X grid. Therefore, we define a function, we call it rates. We have previously in other courses called it dy dt, but let's call it rates for now. Since I don't know what is going into the function yet, I will start with having it empty. The first thing we need to make in the rates function is the derivatives. We need to define it. And we know that the size of the array of derivatives will be the length of the X grid. So this creates 101 derivatives that are all equal to 0 to start with. Good. Now we will define what the last index is in our array here. So that would be the length of the X grid minus 1. That corresponds to the last index position, and that is because the length is 101, but the final index of the last point is only 100 because we are starting at index 0 in the other end. Now we have to estimate the derivatives for all the interior points. We are not going to handle the boundary points, so that would be at the very left side at index 0 and at the very right side at index n. So to do this, the easiest way to intuitively understand it, I think, is to make a for loop. And the for loop is going to be from index 1 to index n. But remember that in this range function, the stop index x is exclusive. So it will go from index 1 to and inclusive n minus 1 if you do this. And we know from theory about how we can discretize the second order derivative here. Remember that dc dt is equal to this second order derivative. And if you use finite central difference, you have a formula for how that is defined. And we will write it here. That is equal to this. And then we need, of course, to multiply by the diffusion coefficient. And we actually forgot that up here. It's like this. Sorry about that. All right, and that is the for loop, and we return the derivatives dc dt, and that is how the function will look. And I get an error here, and that is because it doesn't know what c is currently, and that's because I didn't give it any input parameters yet. So the rates function will take t for time, c for the state variable, and then it also needs to know what x grid is, because we use that here. And it also needs dx, the step size in space, which is used down here. Finally, we need to solve the whole system of derivatives here with the solve IVP function. And this is where we are going to pass the function. The first argument is fun. That would be rates in this case. We also need to define a t-span, which is the amount of time that we want to simulate this over. Remember that we are simulating the development of the concentration at all these positions on the pipe, but also at some time span into the future. So we start at 0 and we then type Tmax here and define how long time we want to run it here by saying Tmax is equal to maybe 1000 seconds. The next thing we need to do is we need to have the initial values. But we have not defined the initial values yet. In the introduction, I said that it should be 10 to the left side, and all other places it should be 0. And of course, if you have 100 derivatives, which we construct down here, each representing the change at the different positions, we also need 100 initial conditions. So the initial conditions needs to be an array also. We call it C0 is equal to like this. And then on the left side, which will correspond to the first initial value in this array, we will set it to 0 like this. And now we can pass the initial values as C0 here. The method we will just stick to RK45, which is the default, so we actually don't have to write it. Then we need to say what T-eval is. So that is the different time points where we want the solution to be returned to us, even though the solve IVP function solves it at many more time points. It only returns these specified time points to us. We will make it with a length space function from 0 to t max and with maybe 50 internal points. Finally, the rates function needs some arguments in order to work. And we can actually just go up here to the range function and see what arguments that is. That is, besides t and c, which is kind of given beforehand when we use this function, it needs x grid and dx. Let's try to run this function and see if this works. It ran with no error, so that's good. Now I will try to plot the results. And I will do this in a for loop because I will plot it at the different positions and over time. So I will start from position 0, end at position 100, and take an increment of 10 for each time. By the way, let's first take a look at the output from the solution so you can understand why we need to do this. So this is the y, which is the solution, and you get all the complete solution by looking in this array at the different positions and at the different times. And you can see here out to the left, we have 10 to start with on the upper left corner here, which is the initial condition, and all other points are at time 0, they are equal to 0. And on the other dimension here, we see that on the left side, it continues to actually be 10 during the whole simulation. Yeah. So if you were in doubt what dimension is the time and what dimension is the position, the spatial, you can actually just try to count the number of rows here. So if we go down, it's 100. And if you go to the other side here, it's only 50. And I just specified that we wanted the solution at 50 time points. So we can know that this dimension here is the time dimension. Time increases in this direction to the right. Good. We now want to plot each of these time series, but we don't want to plot all the 100 positions. We just plot every 10th position. So we take this one first, then we plot this one, and then this, and so on. Okay. This can easily be done in a for loop. We just do like this. And select I here as the index. Then we can also label it with I so we know what's what. And we can add some legend. And on the y-axis we will have the concentration. And on the x-axis we will have the time in seconds. Let's try this. Okay, this is how the final solution looks. We see at the left boundary at position 0 we have a concentration of 10 all the way through the simulation. And because this range function is exclusive, we only get to position 90, which is down here.